All right, we're going to start 15.2 here. We're going to start looking at double integrals over general regions. Previously, we were doing them just over rectangular regions, but now we're going to get more into what happens if it's bound by something more like this, where it's not just a rectangle that we're breaking down, but we're breaking down a general region. The good news is the idea is still just the same. It's breaking into slices. The bad news is it's just a little more complicated to set up the bounds of the integral, whereas before it was pretty easy. You just picked how far it went in X and how far it went in Y, and those were your bounds for your rectangle. Here it's going to be a little different because the boundaries are going to be a function. All right, so if we look at this, we can see we're doing the same sort of thing. We're taking slices either along the x-axis in like in different planes through the x-axis again, and then integrating across y, or we're taking slices in y and then integrating across an x after. So it's still the same sort of idea. It's really just the limits of integration that are going to change. And so if we look at one like this, we can see here for x, we're just having it go from A to B, so it's still going to be flat on those sides. But for y, we're actually integrating between these curves here, between these two curves that are not necessarily just flat on the sides. And you do this by actually putting those curves as your limits of integration, so that as you move, where we moved before, when we went in here and did a slice, right? It was a rectangular slice and it always had the same width at every step you go to. Now, as we step to different places, it's going to end up changing widths based on whatever the value happens to be of the functions between those two at that moment. It's kind of like when we wanted to find the area between two curves. You know, if you had two curves that cross like that and you wanted this area in here, what you were essentially doing is finding this top one and then finding the difference between them, right? You'd find the difference between the two functions and go through and add it up like that, rather than finding the whole thing all the way down to the axis. So you can think of it a bit that way if you like, if that helps. But essentially, we're integrating through functions. So if you're integrating y first, you're going to integrate over functions of x, if you notice that right there. And then you'll end up with a function purely of x to integrate over in dx. So here, after you do the first integral, you're definitely plug numbers in or plug the equations in for it and come up with your next function of just x in order to do the next part. Conversely, if you wanted to integrate on x first instead of on y, you would integrate over functions of y and integrate over x then. And so if you look at this, we have a function of y here, right? Like a function of y, and we'd be going through and integrating across it. So it would determine the width of our slices going that way, okay? And so again, the trickiest part of this is figuring out which way you want to do it, which do you want to do, or not which way do you want to do it, but what are those actual limits of integration that you're going to use in order to do this. All right, so let me pause real quick and see if we have any questions. All right, so basically we can go through and it doesn't really matter which way you do it. If you want to integrate it over x first and then over y, then that would end up being fine. And again, I know it seems a little weird that we are still integrating a volume with an area type of integral, but again, you could do this like one more step, which we're doing is you could actually change this over and say this was like an integral for this area, right? And then we could add on an integral for z, where we went from 0 to f of x, y like that. And then this would be a dz dy dx type of a thing. And then you'd have like a function of x here and a function of x here, and then just an a and a b here. And so it actually is a full type of integral where we're doing that little volume element. It's just that our volume element is dictated by this function. And after you take that first derivative, you know, as soon as you take derivative of z, you've immediately got this step right. You have the function now in there and you only have two integrals left. So that fits a little bit better with what I was showing y'all yesterday when we did that sphere. So anyway, we go through cut slices. So if f of xy is positive and continuous over R, we define the volume of the solid region between R and the surface z equals f of xy to be that, that integral there, the areal integral, as before. If R is a region like the one shown in the xy plane in the figure 13.9, bounded above and below by the curves g2x and g1x on the sides of the lines x equals a and x equals b, we may again calculate the volume by the method of slicing. So in other words, we are doing the exact same thing, but we're just making our limits of integration these functions here. All right, and so that's really going to be the only difference. Okay, and so I lost my train of thought here. Okay, so that's really the big difference. Instead of just integrating from constant to constant, we're integrating from a curve to another curve. And those curves then will change how wide our slices are cut according to what they are. Okay, and so then we can also similarly do it the other way with dx first and functions of y like that. Okay, so let's take a look here. Here is the theorem again, Fubini's theorem, just a more, I guess a more general type of form of it. So if R is defined by A, or X is between A and B, and Y is bound by these two functions, then we can go through and do the integral there, doing, of course, Y first. And then conversely, if we bound Y by constants and we bound X by two functions of Y, then we can do this version down here where we have we're integrating over functions of Y, we're integrating X over that, and then bounding them with Y, and then integrating over Y. All right, and so let's go through this first example here. So it says, find the volume of the prism whose base is the triangle in the plane, or in the xy plane, bounded by the x-axis and the lines y equals x and x equals 1, and whose top lies in the plane z equals, or f of x y equals 3 minus x minus y. So here in the first one, we're going to go through and do the integral over y first. And I think there's a picture of this on the next page. So if we're doing over y first, what you can see is we're going from 0 to x. Because if you look at that triangular base, which we've got a picture of right here, as we integrate across y, the width that we're drawing here goes, where is it? Goes from 0 out to x, like this. And so if we start over here, we start from 0 to 0, and then whatever x happens to be, we keep integrating up this way, like that. And then, of course, any single one of those we do gives us something like that red line, where y goes out to equaling x. And then we, of course, integrate from 0 to 1 on x to then go through and do each slice. So we start with this slice, and then we, as we get a function for that, we keep integrating along this way and adding up the slices that way. And when we do that, you can see it right here. We go from 0 to x, and so you integrate that from 0 to x, you plug in 0 to x, and you notice here we end up with a function purely of x then at that point. And then we integrate that simply from 0 to 1. You can go through and do it yourself, and we get x equals 1. Conversely, we can swap the order of integration, and we'll integrate for dx first, for x. And if we go back over here and look, when we're integrating for x, notice here we're going from y out to 1 there. And you can see that here, that's where we're going when we go this way, because this is the y equals x, and the y equals x, and it goes along in this fashion right here. And we go out from y, when x equals y, all the way out to when we get to it equals out here at the 1. Of course, for dy now, we're still going 0 to 1 because that's what we're going to up there as well on it up there. And you just kind of go through and you do them. And again, you do the integral for x first, you plug in the y's for it, you get a function of y, you integrate it on y, and you get a different thing. Now, you might notice that this version up here, the first one was only 2 lines long, the second one's 3 lines long. Sometimes doing it in one order is simpler than doing it in the other order. And so you'll want to take advantage of that where possible. So let me pause for any questions here. All right, so moving on to the next thing, take a look at this example here. We have calculate this volume here according to, underneath this single function here, where R is the triangle in the XY plane bounded by the x-axis, the y-axis, and the line y equals x and the line x equals 1. So this is actually the same boundary as the previous problem. It's the same triangle, but we have a different function that we're integrating underneath. So we should get a different total volume here. In other words, it's like we have the same triangular, like say we had a triangular slab of concrete and we essentially we changed the roof out here. Over here, we had one particular roof, which was just a slanted roof. And now we've replaced it with this sine x over x roof on top of it. And we have a different shape there. So if I go through, you can see here on this first one, that was supposed to be an X right there. Doesn't really look like an X. But the very first one I did right here, this one, I went through and I integrated on dy first. And so that just takes me from 0 to x on y. So that's like taking this one here, taking this slice here, 0 to y. That was that first thing on the first page. 0 out to whatever value of x we happen to have there. That's what y will equal, whatever x happens to be. So if x is 2 here, then this will be 2 or something like that. Well, I guess it can't be 2. We only go out to 1. So if x is 0.3 here, then this will be 0.3. And we'd go from 0 to 0.3. But we're going out from 0 to x. And so I integrate that over y. Well, sine x over x is just a constant as far as y is concerned. And so what do you get? You get sine x over x times y, and then we're evaluating from 0 to x for y. If we plug in x, you get sine x over x times x, and the x's cancel, right? And then you have minus, and you plug in 0, it's 0. So you end up actually just reducing down purely to sine of x. And that integral is then pretty easy. The integral sine x negative cosine x. And then you do that from 0 to 1, and you end up with, I didn't plug it into a calculator, but the negative cosine of 1 plus 1 is what you end up with right there. And so, you can actually get an answer. But if we try to reverse the order, if we try to do on y first, right, where we're going from y out to 1 here, right, like this for x, because here x equals whatever y is, and out here it equals 1. So if we do x first, we go from 0 to 1, but then we do y 0. But look at this integral here. That's a colossal pain. Integrating that sine of x over x, that is not an easy integral to do. And so sometimes swapping the order of integration is actually very beneficial in that it allows you to do an integral that's more difficult, I guess, is an easier way. So you do want to be careful if you pick an order that you do this in and it turns out to be a really difficult integral. The lesson here is sometimes try reversing the order of integrals that you're doing, which requires you to change your actual integration order or your actual bounds of integration, but it can also end up letting you do the integrals in a way that is much simpler than it was before. Now here it wasn't that big of a deal. I mean, yes, this one was a little bit easier than this one, but over here, it's a very big difference. And actually, I just noticed I wrote this backwards here. Hold on. That should be 0 to 1 there, and that should be y to 1. Sorry, I just flip-flopped that. So anyway, that's a nice little example showing that it can be much simpler to change that order. So let me pause real quick. All right, so let's move on and let's talk here about finding the limits of integration. You can see here, there are some nice pictures showing this. If you're going to look at this, you can see here, they're showing you, we're doing between these two curves here, x squared plus y squared equals 1, which is that circle, and then the x plus y equals 1 right there. You can see that as we go through this, we are entering into it right there and leaving it right there. So that's what our bounds would be. This would be your lower bound. This would be your upper bound type of a thing as you go through and do this. And so this would be, you know, the way you would find it doing this integral, which I think I kind of showed back here on this page, right? When we integrated it over here, right? We set this one up to integrate on y first. We did it from 0 to whatever y equaled then on x. And so the same thing here. We're setting it up to integrate on y first, and then integrating after that, you'd go through and integrate with respect to x. And so x simply goes from 0 out to 1, but y goes from 1 minus x up to square root of 1 minus x squared. And so if you just draw yourself a little picture like that, that'll help. Conversely over here, same picture, but you can see it enters here and leaves there. So if you're going to integrate with respect to x first, the bounds for x would be to solve that function for x equals, so, you know, as a function of y, x as a function of y is what you're essentially getting there. You're going to go from 1 minus y out to square root of 1 minus y squared, and then y itself is just going to go from 0 out to 1 on its bounds. All right, so that's essentially the way you're going to want to try and fix these up. Feel free to draw yourself these cross sections if it helps you come up with these limits of integration. If you can't picture it quite in your head, then feel free to do that. Here is a quick little example of this. It says, so sketch the region of integration here, write an equation with an equivalent integral with the order of integration reversed. So I'm going to let y'all try that. You see here, they're integrating on dy first. So that was them originally taking this kind of a cross section, but they've drawn you a picture here for it. So go ahead and write that down. I'll give you a second to write down what this integral would be if we were integrating with dx first. So I'll pause and let you do that. All right, so hopefully you had a chance to write this down, but essentially, and I don't think it's on the next page, is it? No, just making sure. Essentially, we're going to do still a double integral, but this time we're integrating over x first. So we're going to have functions of y. So we'll go from y over 2 to square root of y. And then for x, we're just going to go 0 to 4. Or I'm sorry, for y, we're going to go 0 to 4. We have our same 4x plus 2 here, and then a dx dy. All right, and if you were, and I'd recommend to you, go through and try both of these integrals, both what we have there and the other, and see if they work out to be the same value. All right, so continuing on here, I think this is just a way to type it into some computers or something like that. If you want to actually go in and do this, I think you could even type these in pretty much in this form into Wolfram Alpha if you wanted and get these other ones. So more interesting here is some of our properties that go along with these double integrals. Of course, some of these just extend right out from what we've done before. If you have a constant multiplied onto it, you can bring that constant outside, just out in front of your actual integral. The sum and difference of two different functions, you can separate them and integrate them separately. So again, similar to what we've done before. Here, if we know that our function is greater than 0 everywhere on our region, then we know that our overall volume will be greater than 0. You have to be careful with this because, again, volumes that go down below where the region is actually negative are going to be like negative volumes. So you could even do something different like this. If it was less than 0 everywhere, then we'd have a volume less than 0. And then here we can say that if we know everywhere on our region that f of x is greater than g of x, then our total volume over the same region for f of xy, sorry, would be greater than g of xy. And then of course the additivity, I'll get it out. Here, if we can break this up into two different regions, so it's similar to what we would have had before, where if we had like a function like this and another function like that, that we could actually split this right here, and we could do, oops, I thought I changed colors. We could split this right here, and we could integrate from A to B, and then from B out to C. And so we could have just done the integral from A to B and gotten it of some function minus g of x like that. But we can also split this up into an integral from A to B plus an integral from B to C. And you can do that same sort of thing here. You can split it up into different regions. If you have certain bounds and limits that work in one region and then you have to change them as you go to another, it can help you do things that you maybe would have trouble doing otherwise. And there's a picture showing that right there, where you could have this first region and the second region, and you could do them separately. So this whole region, which would be R, which is that union of R1 and R2, you could also just do R1 by itself, R2 by itself, and add them together, assuming the regions do not overlap. If they overlap, then you'd have to like take off where they overlap, kind of a thing, which might become quite cumbersome. But if you have two regions that don't overlap and they're like that, the total for both regions, the total volume for both regions, and even the total area for both regions would just be these separate integrals of each. All right, so let's take a look here at this example, and I'm going to pause it and give you a moment to take a look at it. And I think I had one, yes I did it right there. So this is right here near the end, and I want you to go ahead and try this one.